In this video, we're going to take a look at how to take a combination of resistance and reduce it so that we can find an equivalent resistance and then work our way backward. So we have our friends voltage, current, resistance, and power. Again, it's important to have a model in the back of our head. Voltage is energy. Current is the physical particles that carry the energy. And then power is the rate at which energy is dissipated. So when we take a look at 12 volts, we've got plus and minus. So conventional current is going to flow this way. And I'm going to call that I1. But then when the current comes back, then it's still only one pathway to make it back here. So this is still going to be I1. So the current through R1 and R2, we're going to expect to be the same. So I'm just going to put a little box around here, a red box. We're expecting these two currents to be the same. Then we have a place where the paths split up. And this crazy one that goes at a diagonal is just meant to kind of fool you. But the current is going to split up into 4 different ways. So we'll have some current here. I'll use a different color for that. Let's try purple. So now the current's going to split up. Some will go this way, some will go this way, and some will go this way. But then you can see it all comes back together because this current is going to do a UE right there. This current is going to swing the corner, and this current's going to come back. So they're all going to meet up again. And this is actually one of Kirchhoff's laws. So the current entering a junction is equal to the current leaving. And so that's why these two are both I1. Now, when the current splits up, we notice that the resistances are all equal. Drawing this diagonally is really, I could have drawn it horizontally. It would have been fine. The main thing is that each one of these resistors has a common point here and a common point here, a common point before and a common point after. So that means that these are all in parallel. And what that means is that they're all going to have the same voltage drop. So I'm going to do a purple box around these. They're all going to have the same voltage drop. But now in this case, because the resistances are the same, they all have the same current, which is more of a coincidence. But these two elements are in series with each other. That's how come they're going to have the same current. And these three all have common points before and after. So our clue is single pathways means series, and multiple pathways means parallel. So I can redraw the circuit, and that's actually the key for this equivalent resistance, is that we can redraw the circuit, and now we'll still have R1, and we'll still have R2. But then we can replace all three of these with an equivalent resistance that we can determine right now. So in parallel, we add their reciprocals. So 1 over Req is equal to 1 over 18 plus 1 over 18 plus 1 over 18. Well, that's 3 over 18. And that's the same, 3 over 18 is the same as 1/6. So our equivalent resistance is 6 ohms. And now we have, well, R1 and R2 haven't changed. So this is still 4, and this is 6, and this is 2. That makes a total resistance of 12. And so that's what the source sees, is 12 ohms. And 12 is a nice round number. So V divided by R gives us our current. So that's 1.0 amps. And then 12 times 1 gives me 12 watts. Okay, now let's take a look at the rest. What's happening? Well, the current from the voltage is the same as I1. So these are both 1. And then I can multiply things out. So multiplying by 1 is easy. 1 times 4 is 4. And 2 times 1 is 2. So this is going to be 4 volts and 2 volts. And that leaves, if our charges start off with 12 volts and they lose 4 here and they lose 2 here, that means that they have 6 left to leave here. So all these purple boxes are 6. And between Ohm's law, P equals I times R, and the power relationship, P equals voltage times current, once we know 2 things in a row, we can figure out the other 2. So let's finish up with doing the currents. So V divided by R, so this is going to be 1/3 or 0.33. 0.33 repeating. And so this is essentially 1/3. So 6 times 1/3 is going to be 2 watts here. 2 watts here, 2 watts again. And then 4 times 1 is 4 watts. And 2 times 1 is 2 watts. So in the grand scheme of things, this one is going to be the brightest because it's got the most power output, if it's a light bulb, for example. And then all the others are going to be equally bright. Let's check out the totals here. 4 plus 2 is 6, plus 2 is 8, plus 2 is 10, plus 2 is 12. And that's simply conservation of energy. So these need to total up what the battery is producing because this is conservation of energy. Okay, great. Well, I hope that helps.